Hey everyone, welcome to the webinar. We're just waiting for a few folks to trickle in. We'll get started shortly. In the meantime, maybe we can quickly intro ourselves today. I'll go first. I'm Chinmay Soman, a VP of Product at StarTree. Nice to meet you all. Uday.
Thank you everyone for jumping on. I'm Uday. I run the R&D team here at StarTree. Looking forward to the session here. Thank you. Do we wait for a couple of minutes, Chinmay, or can we get started?
I think we can get started.
Okay. Can you? Yeah, perfect. So thank you everyone for jumping on today. Chinmay and I, we work for StarTree. StarTree it provides an enterprise grade managed service for Apache Pinot. In today's session, we'll do a quick introduction to Apache Pinot, its origin story, what was the key problems it was solving when it was created, a little bit on the original architecture, but we'll spend a lot of the time today talking about new capabilities that we've added to Pinot around external tables, being able to query data from a warehouse, from object store directly, right? Now, what is Apache Pinot? I'm assuming a lot of folks know what Apache Pinot or heard about Apache Pinot, but I'll give a quick introduction. It's a real-time distributed OLAP database, right? It was created at LinkedIn just around the time or a little after Kafka was created. It's same groups that kind of created this, and StarTree is founded by the two original creators of Pinot, Kishore and Shang, right? Now, the key problem that Pinot was trying to solve, or LinkedIn was trying to solve, was to build a system that can provide extremely high concurrent query throughput, right? That's the key problem that LinkedIn was trying to solve. And they wanted to make sure that the data freshness aspect of the queries is maintained while also providing interactive latency. That's kind of a mouthful, but those are the three tenets, right? High concurrent, extremely high throughput queries with real-time freshness and interactive query latencies, right? And the key design goal was to make sure that we are able to do this with as little work done per query, right? And as you go through this session, that's a key theme that you will observe is Pinot is centered around reducing your dollar per query, right? Originally when Kishore started the company, that was kind of the ethos for StarTree also, is to make insights cheap enough for our customers so they can provide to their customers, right? So that's kind of the central principle for Pinot and for StarTree, is to really reduce your dollar per query, right? Go to the next slide, Chinmay, please. So Pinot, like I said, was created at LinkedIn, and one of the first use cases that Pinot was built was, the Who Viewed My Profile app that LinkedIn has, and that's one of the things that actually really propelled LinkedIn's adoption. Right, they gamified the entire, professional network landscape by allowing people to see who is actually interested in them and things like that. Right now, when Pinot, during its inception, LinkedIn was 50, 60 million users, and it kind of grew to few hundreds of millions of users. And Pinot was able to sustain that throughput and be able to provide that real time insights back to every user that logs into LinkedIn. Right, tens of millions of users are using this app, and that's all powered by Pinot. Right, and later on, Pinot was adopted by Uber, Stripe, and lots of other companies. So the way I think about it is, if you ever used LinkedIn, a lot of the stuff that you see on LinkedIn is coming from Pinot. If you ever used Uber Eats, DoorDash, Zomato, Blinkit, any one of these, logistics, companies, they are using Pinot, and you are using Pinot when you're using them. Stripe, for example, uses Pinot to track all of their transactions. All of Stripe's transactions are tracked. What you see there, that little widget is, Stripe built that dashboard to show the transactions during Thanksgiving or something, and it kind of, shows that they were able to keep up with the data that is coming in into Stripe, right? And the use cases are also quite varied, right? LinkedIn uses it for user facing, Uber uses it for operational intelligence, and Stripe for different use cases, and a lot of other companies that are using Pinot. If you go to the next slide, Chinmay. So when we started, for example, 6 years ago, there were maybe 5 or 6 companies using Pinot. Now, at least 2,000 companies that we know of are using Pinot in production, right? If you look at the names, if you ever purchased anything at Walmart, if you ever used Slack, Nvidia, Activision, the list goes on. All of these companies are using Pinot for their real-time analytics. And with StarTree, what we've done is we've created an enterprise-grade managed service that we provide to our customers. At StarTree, we have both BYOC and SaaS. BYOC is essentially a bring your own cloud deployment model, where we deploy inside your VPC, so there is no data movement, and we have the standard SaaS model also. And over the last 6 years, we've seen phenomenal growth. Really proud of how Pinot has grown over the last 6 years. You can see some of those numbers there. And the companies is the companies that we know of, right? There's this more than 5,000 companies in the Slack community that we have, and Slack also uses Pinot, as a matter of fact. The ones that we know of are around 2,000 companies that are using Apache Pinot or StarTree in their production environments. Go to the next slide, Chinmay. I want to touch on the scale at which Pinot and StarTree operates at some of the customers. Right? These are not, aggregate numbers. These are, a single cluster. For example, we have one customer who's a telecom provider, and they have a StarTree cluster where we see, upwards of 100 million events per second that we are able to ingest and provide query throughput to them. Right now, it doesn't mean that just because we are doing 100 million events per second, the queries can be delayed or the data can have a lag. That's not acceptable. So that's just one cluster, right? It's like, I think, a 300 node cluster or something like that. Right? We have the middle one is the last we know about LinkedIn. LinkedIn has probably the cluster which has the highest query throughput. The cluster at LinkedIn, last we know of, is running around 250,000 queries per second. That is QPS, and almost all of LinkedIn's workload is user-facing. Right? If you use LinkedIn, the feed that you get, all of the numbers, the number of likes, number of shares, all of that data is coming from one single Pinot cluster, and that is what is driving this query throughput. We have another customer where talk about data freshness. If the ingestion lag from their Kafka topic is greater than 5 seconds, that's considered a P0 for them, right? That's the tight SLA that we maintain for that particular customer, right? Now, 1 and 3 are StarTree customers. The middle one is clearly LinkedIn. They're a big proponent of Apache Pinot. At StarTree, we have upwards of 200 clusters that we manage. And I think the last Chinmay told me the number was around 10 billion queries per week, Chinmay, that we run across our fleet, right? So across our fleet, which is 95% or 90% bring your own cloud deployments, we run around 10 billion queries per week. So pretty large footprint that we operate and manage for our customers. Now, the reason why I'm showing this is, two things. One is to underline that Pinot is built to handle the scale, right? But that's not all. We have some customers with a very small footprint, and the reason they picked Pinot was because of the efficiency, right? Like I said, the central theme for Pinot has always been dollar per query. How do I reduce the dollar per query for our end users? And you don't get this kind of scale without building that efficiency natively at a foundation level in the database itself. And that is what really puts Pinot apart from the other solutions that are out there. Right. Go to the next slide, Chinmay. So traditionally, Pinot has been a tightly coupled architecture, right? Your storage was co-located with the compute and heavily distributed, right? You have the typical architecture. You have brokers, you have data carrying nodes which are called servers, and you can keep adding more brokers and more servers as you scale. Now, Pinot relies heavily on indexes to essentially reduce the amount of work you do for answering the question, right? What is the total number of users that logged in the last 1 hour? Well, I don't want to actually do the count. I want to come up with a shortcut to be able to answer that question. That is where all the indexes come in. Now, if you recall the previous slide about the number of companies that have used Pinot or that are using Pinot, the number of indexes is kind of a testament to the wide range of use cases that Pinot is getting applied into. Right? We have the usual, inverted index, sorted index, range index, and all of that. I think Chinmay will cover some of those things. But we also have, geofencing index. We have a, vector index. We have that range of indexes allows you to address the right index for your right workload, right? And it's all tightly coupled. Since the middle of last year, we've invested in what we are calling as external tables. And with external tables, what we have done is we've decoupled the storage and compute. We actually started this journey around 3 years ago with our tiered storage implementation that has been running in production for a lot of customers over the last 3 years. And we've kind of taken it to the next step where instead of using the tightly coupled Pinot native format, we are now converting that to an open table format, right? So, essentially Parquet. In this model, in the external table model, we don't actually move the data. The data sits in your data lake. It could be Delta, it could be Iceberg. And we create indexes on top of that data, which also stay in some kind of an object store. And we are able to provide queries at the same kind of latencies that we're talking about, right? So we are still able to do sub-second query latencies. We are still able to do 500 plus queries per second, but now the key difference is there is no movement of data. Almost all of our existing customers, they are working with high value data and they are moving it into Pinot because they are providing those analytics. Now we are getting into a space where they don't want to have another copy of the data. The data that's in the lake is staying there, and we want to provide that same Pinot StarTree SLAs on those queries, right? So the next section, Chinmay will talk about how we are actually able to do these sub-second queries with 500 QPS without actually moving the data, without doing all of the things that Pinot was known for doing, and still be able to get the same SLAs. Thank you. Chinmay, go ahead.
Thank you. You can hear me okay with that?
Yeah.
Okay, perfect. All right. So, before we go deep into the external table, I did want to talk about the Pinot architecture and how that works under the hood. And then I think it's easy to understand the journey from how we moved from a tightly coupled local storage to a fully decoupled remote storage on Delta tables and Iceberg tables. So let's begin with Pinot first. Right? Pinot was really built for the three main things, right? The real-time ingestion, being able to serve analytical queries on events as soon as they're generated, right? As Uday already spoke about. And then the second is the distributed architecture. This was designed for terabyte, petabyte scale data, so you can scale out as much as you want, but that query performance is still predictable in the presence of organic growth. And of course, indexes. Right? I'll talk more about this, but the whole point of Pinot is to do the least amount of work needed for answering questions. Right? And this is where indexes are critical. And we do leverage them everywhere, including on external tables, as we'll see. So let's take a quick look at some of these things, right? so Pinot is able to ingest from various sources like Kafka, Kinesis, Pulsar, and so on, and it ingests data in real time and within seconds and converts them into what we call as Pinot segments. And these Pinot segments are distributed across the different Pinot servers. So in the vanilla Pinot architecture, these segments were local to these servers. So this is what we mean by tightly coupled. But in this case, we were able to do more than 100 million events per second, highly fresh data, and the most important part is support for upserts and deletes. Pinot is one of the very few real-time OLAP systems that can do upserts, dedupe, even partial upserts in real time within seconds, without any asynchronous compaction. And the other big thing is it was designed with Lambda architecture for the same real-time table. You could push the data from a different source like S3 or even Snowflake or Delta table into the same real-time table and then do a full spectrum analysis across the real-time and historical data, which is transparent to the user. So this was sort of the design philosophy, and that's what's going to help us in the external tables as well. In when we talk about query execution, how does Pinot get all the 250,000 QPS and sub-second latencies? Again, the main philosophy here is reduce the amount of work when a query comes in. So what this translates to is we have data spread out across multiple servers, across multiple segments. So what we need to minimize the number of servers we need to talk to, minimize the number of segments that need to be processed within those servers, and then further down at the segment level, how many rows do we need to actually fetch to answer that query? Right? That sort of the optimization happens across all these levels, right? So when a query comes in, Pinot Broker is a component that does a distributed scatter gather across the Pinot servers. So at a broker level, without even talking to the servers, it leverages the metadata to prune a lot of the segments at this stage. So for example, if the data is partitioned on a certain set of columns, it will, and that's being used in the query filters, it can leverage that to say, out of these 12 segments, I only need to look at this subset of segments, right? Based on partitioning. Or this could also be time-based pruning. So if you have time filters in your query, we do have a time column for every Pinot table, and it can use that to filter out a large group of segments. So it does not have to process this at any point. Contrast this with traditional engines, which typically, they do apply partitioning to a certain extent. And so some of this is common, but not all systems do this. Another one is Bloom filter. So now we know which servers we need to talk to, and within at a server level, we can further employ Bloom filters to say whether the data exists in the corresponding segments or not. So this lets us further prune away segments from those. So initially we came down from 12 to about 6, and then we further went down from 6 to, let's say, 5 in this case. And Bloom filter is also another commonly used things across this. This is something we also leverage in Pinot. This is where I think the differentiation starts kicking in, right? So now we know exactly which servers we want to talk to. We know exactly which segments have the data. But again, most query engines out there will simply scan these segments and then try to process the query. So Pinot is able to do one more level of pruning at a segment level. So for each segment, it leverages indexes to find out of, let's say, if a segment has 100,000 rows, it can selectively only scan, say, 100 rows from that large set to answer a query. So for highly selective queries, if you have queries with filters on a particular column, this becomes extremely useful, right? So we are trying to minimize how many rows we need to scan. So in this case, the segments are stored locally on the servers, right? So scanning is not that expensive, but you can immediately see as soon as we move the segment, or if you're querying a Parquet file sitting remotely, minimizing how many rows to scan, that's critical for the external table query performance. Talking a bit about the indexes, right? So at each segment in Pinot, you could configure any of these indexes on any of the columns in your schema. So if you have, Pinot can support hundreds of columns in a schema, and there's various types of obviously column types. So you could use inverted sorted range indexes on the numerical columns. So this will help in lookup use cases, or anywhere with range query scans. They can be accelerated using these indexes. We also have a geospatial index. If you have, if you're using geometry, finding a point and polygon style queries, those are accelerated using the H3 GeoIndex. Similarly, we have a text index and JSON index for unstructured data. Vector index was added about 2 years ago. This is actually very useful. You could natively store embeddings as one of the columns in your Pinot schema, and then do similarities or semantic search using the vector index on the data. And then finally, we have the StarTree index, right? This is one of the most powerful index in Pinot. This lets us do some sort of pre-aggregation on a bunch of columns and a bunch of predicates. So the query time cost is extremely slow. Note that this is different from materialized view. This is actually much smarter than a materialized view, because it does not do full materialization. It actually gives you the trade-off on cost versus latency. So we have all these indexes, right? Currently in the vanilla Pinot, these sit next to the local segment on local disk and accelerate queries, right? So the result is, let's say we have thousands of servers, terabytes of data. At a per query level, we can narrow, without even doing the first scan, we know exactly which segment on which server to process, and within that, I only need 100 rows, no matter how the data grows. So the effect is, the data can keep growing, your number of nodes can keep growing, but the query performance stays predictable, and that's how we're able to achieve this at the scales Uday had mentioned before. So let me switch gears a little bit now, right? How do we take the strength of Pinot, which was really built in LinkedIn, built for tightly coupled storage? How do we translate that in today's world? And today's world looks very different, right? The open table formats have really revolutionized analytics, large data analytics, right? Uh, so, namely Delta Lake, Iceberg, and Hoodie and others, right? These have enabled all companies to store data in an open protocol, which any query engine can talk to. So now you don't have to be locked into one vendor. You can control, or you can basically have all your company's data sitting in one of these data lakes, and then choose what query engine you want to run on top. So you may be able to run, for example, on the same table, you can run Spark or Trino for some complex ETL workloads, or you could run Trino for some interactive workloads. And then our proposal is to have StarTree to run your low latency workloads on the same table. So one differentiation where StarTree stands out, like if you think about the traditional compute engines on data lakes, right? The philosophy was to parallelize, right? So if something is slow, you add more compute, more parallelism, and you drive down the latency. And this indeed helps, right? This helps to bring down, say, if you have one worker takes whatever 60 seconds, you can parallelize 10x, and you would somewhat get a linear improvement in performance. But the issue is, if you have to do a lot of these, imagine trying to do fraud detection on your Delta table or Iceberg table, which can easily be 100 QPS or so, and every query has to be a sub-second, right? You could build this on traditional engines, but what will happen is the query cost, right? Because you're throwing in more compute, more parallelism, and this is some of these are always on workloads, your cost is going to be exponential and not linear as more and more of these workloads go on, right? So open table format solved the storage cost problem. Right now we can everyone can choose the most optimized columnar format for storing data, but the query cost is still a big open problem, and that's what we want to address with StarTree. So what StarTree's mission is to leverage Pinot's best capability, which is indexing, and apply that directly on data in data lake and delta tables and iceberg tables. Um, so this is how the new architecture looks like, right? So we still have brokers and servers, but as you will see, the servers here really act as a hot cache layer and not the storage layer. So in this case, the data is stored on one of, let's say, Delta Lake, Delta tables or iceberg tables through some catalog, and the raw files are in Parquet format, stored in some cloud object store like S3 or GCS. So the first thing we do is when we onboard a new table, we actually go ahead and proactively onboard all the metadata right up front. So this is a little bit of a cost that we are paying at onboarding time, but this is what actually makes our query processing much faster, because we don't have to do the discovery at query time. So we are shifting a lot of the metadata discovery, metadata optimizations from query time to the onboarding time. So for example, the column metadata, all the statistics are we already know even before the first query is fired. Then the other thing we obviously do is on any of these columns in your data lake schema, you can now configure any of the indexes I mentioned before, start index or numerical indexes or even text or JSON index. And then as part of this onboarding, we are building these indexes on directly on the raw data. And these indexes also live in the remote storage, right? It's not stored, and none of that is actually stored locally. So Pinot now becomes like a pseudo stateful query engine sitting on top of your data lake, right? So where do these Pinot servers come in, right? So as we execute queries, what we are doing is we are obviously leveraging indexes. So some of the indexes are brought into the local persistent cache on the Pinot servers. And alongside, we also bring a subset of the hot data that's being accessed by the queries. So eventually, as these queries warm up, we warm up the persistent cache in the Pinot servers, right? So the hot set, especially the indexes, help us do predictable query latency even for data sitting in the data lake. Right. So in general, the query optimization looks very similar to what I described before for vanilla Pinot. Right. A query arrives, we use metadata-based pruning to prune away most of the files or segments that we need to process. We use indexes to further narrow down which portion of the Parquet file we need to scan. Right. So Parquet file, for people who know, is divided into column chunks and pages. And so we are able to selectively do which specific page within a Parquet file is relevant to the query that we got, and only scan those. So the whole point of query optimization for external tables is to minimize scans from the remote object store. And then this is what makes a huge difference, right? So we have, just to visualize this broker level pruning, you have all the Bloom filters can still be cached locally on the Pinot servers. And then all of these indexes can also be cached locally on the Pinot servers, which really gives us the boost in performance. So if you think about what's happening with traditional query engines, right? Like if you think about Trino as a representative query engine, they all do partitioning, they all do Bloom filters, but then when it comes to these Parquet pages, they need to download or scan these Parquet pages locally, and then do the processing on local compute. So you're bringing in, for this is just an example, but you are bringing in a lot more data on the local processing nodes. Contrast this with Pinot and StarTree, we are able to do an order of magnitude, sometimes lower data scans. And where this helps is we need fewer nodes to process the same query, which translates to lower CPU, lower memory requirement, and overall lower TCO for running the same set of queries on the represented data set. So let me do a quick demo for this. Right, this is we did a small data set here, NYC taxi data set. This is a local setup. It's the NYC data set is sitting in S3 in Parquet files. And for this demo, I leveraged Trino and obviously StarTree. These are running as Docker containers locally. And they're both trying to do the same set of queries. Let me switch to this one. So are you able to see the screen Uday? Just to make sure.
Yes.
Okay. All right. So I picked 3 different query patterns for this demo. One is a high selectivity query. So get a bunch of aggregations between 2 geo points. Another one is a low selectivity query. So you're actually scanning a whole bunch of data to answer a question. So this is expected to be an expensive query. And then the third one is a multi-stage query. So this is running a window function, 3-hour rolling window function, which is directly running on top of the data sitting on the data lake. Right. So let's go ahead and run this. Oh, give me a second. I'll come back to this demo. I think this. Let me just reload. Okay, we'll come back to. I'll quickly go through the other benchmark that I have that we did on a proper setup, and I'll come back and demo this. All right. So that was the local demo. Unfortunately, that did not. I'll come back and hopefully demo this still. But this was a much larger demo that we did using a cloud setup running in EC2, right? So we have, and this is published on our blog. So we started with a 1 terabyte clickstream event data set with 12 billion rows. We used 4 R6GD servers that were running 3 systems, in this case, StarTree, Trino, and ClickHouse. And they were all trying to run the same set of queries, right? So this is published. You can go read this. But what we observed is because of the indexes and all the optimization I mentioned before, StarTree was able to showcase a order of magnitude lower query performance. Right. This is just showing the difference between Pinot local and StarTree with external tables. So the blue and the green is the one to watch out, and they're pretty similar, as you can see. So we are able to match the performance with Pinot local as if the 1 terabyte data set was loaded locally in Pinot. Similarly, on the query side, we have, it is able to, the green is the external table here. It is actually able to match the QPS performance, the same as Pinot local blue line. So this is where we were able to run upwards of 500 QPS on 1 terabyte data set sitting in Parquet. We also did the same comparison with Trino and Iceberg, and as expected, we saw an order of magnitude difference. Trino was bringing in a lot more data for the same sort of queries, and we did obviously apply a bunch of optimizations here, right? Partition data, Bloom filters, FS cache was enabled, but we because of the lack of indexes, really, that's what really gives a big performance boost. Same thing with ClickHouse, similar setup, a bunch of optimizations that we use here for ClickHouse, but we still see, Pinot, the external table for Pinot and StarTree is order of magnitude faster, more efficient than the
And
other.
you have to add that we did borrow expertise from the Trino and the ClickHouse community to make sure that we are not missing any obvious things, right? So
Yeah, and in this blog, we can link it in the chat maybe. This is a very comprehensive blog. If you go through that, Arun, the author, he really did a lot of work to be fair to each system. And you can go through all the optimizations. We have detailed that in the blog. So we tried our best to optimize each system. But yeah, I mean, if you think about on paper, if you're scanning less data, obviously the performance is going to be different, right? So indexes is sort of the key lever here. I do want to highlight one thing, right? From the benchmark, one thing is, because we are, the amount of data being fetched um, is different. So in this, for across the benchmark, StarTree only consumed 4 GB of data over the network from remote S3, right? And as compared to Trino and ClickHouse, obviously, by the way, we made sure the cache is not as big as a data set, just to be transparent. This was intentional to make sure everything is not cached locally. Everybody had the same cache size available. So the one difference we see is CPU performance, right? Because there's less data to process, our overall CPU utilization on the same 4 or 6 GD servers was significantly lower as compared to the others. What this means is, just with those 4 servers, we can actually handle a lot more query load. So if you had to go from whatever 10 QPS that we did before to 100 QPS, StarTree would need far fewer resources than the other systems out there, right? So over that's sort of the message there, right? Reduce the amount of data being scanned, lower your TCO. That's a direct correlation. As you're running these, in a lot of cases, concurrent queries, low latency queries, and typically an always on workload, that's where you'll see the biggest TCO benefit. Just to, we've spoken a lot about Pinot. I did want very quickly touch upon StarTree. So StarTree is it provides a managed cloud offering for Pinot, with different options. You can do it using a SaaS, or most popular is BYOC, where you can deploy StarTree in your cloud account and you control the governance. And obviously, a bunch of our open source users are also StarTree customers, as is mentioned here. So do reach out if you see this useful. We are running a sort of a quick start program. So if you are interested in, if you have a representative data in your data lake, Delta tables or Iceberg tables, we would love to talk to you. We are offering a quick start program where you bring your workload, and within 3 weeks we can show the value of Pinot on your own data. So if this is interesting to you, do reach out to me, or directly reach out to us on startree.ai. And that's it. While we can, if there are any questions, we can get into that while I go back and check on the demo real quick.
Yeah, there are some questions. I'm answering them. The last question was around comparison of ingestion throughput and data freshness latency. There are the blog that Chinmay was talking about that does cover freshness in part 2. That blog is already out there, and there is a lot of ink spent on the ingestion capabilities of Pinot. We have several blogs authored by Chinmay himself, which talk about, and we can share that offline in the next few days. Yeah, so there's blog content already there for comparing ingestion throughput and data freshness for Pinot local. External tables is covered in Arun's blog. Chinmay, or Eli, if we can Arun blog somewhere.
Sure. Yeah. Let me link the blog. I do want to the containers are back up. So let me quickly run this. So I can also go through the queries real quick, right? So just to recap, this is a demo. We are doing side-by-side comparison with StarTree, with indexes, and Trino on the other hand. So for the high selectivity query, we had, for NYC taxi data set, compute a bunch of aggregations between 2 points. What you see here is we are showing the number of rows scanned for that data set. So 39 million for Trino and 16,000 on. So these are actually the exact set of rows that match this criteria here, right? And as you can see, obviously the latency is significantly different than this. The second one is slightly more elaborate, right? So we had a larger low selectivity query. This is just where filter is not that selective. So fair amount, any trip that's costing greater than $50, which is probably, I'm surprised that's not all the trips in New York, but it's significantly more than before. It's 2 million plus here. So as you can see, the number of rows went up significantly. Trino still did the 39 million. And finally, the rolling window, the 3-hour rolling window. This is still a selective query. So even though you're doing joins or window function, this is a multi-stage query, right? We are still seeing significant performance difference on StarTree versus Trino, right? So across the board, you can see the row scanned and obviously direct correlation with the latency here. And the multiplier between StarTree, it's an order of magnitude faster. So the more selective the query, the better performance you'll see on StarTree. So apologies for the first iteration, but yeah, this definitely works. If you have a similar thing, do reach out. We'll be more than happy to try it on your own data set. Let me also drop Arun's link here.
I did drop it there. Chinmay, just make sure that's the one.
Yes,
so there is
that
another question about computation, right? So its question is around, Pinot is able to do better filtering of data, but how about when it comes to calculate the same number of records in all 3 platforms, right?
Let me see which. Oh, I can't see the question. Okay.
Anyway,
is the
go ahead.
question on aggregations on
Correct.
computing?
That's what
Okay.
I was going to. Yeah.
Perfect. Actually, so that's where Pinot does shine when it comes to aggregation. So if you think about aggregations, right, the number of rows we need to process for aggregations versus just doing scans. So if you're just trying to scan data versus doing aggregations, the what all the optimizations I described, right, they are actually more suited for aggregations than scans. Right? So if you're doing, in this demo, I did a sum or average or distinct count HLL. All these are highly optimized in Pinot, and they do work very well with StarTree with external tables. So think about use cases where fraud detection. You want to get aggregate view of something, logins or user activity, user behavior. This is actually a perfect use case for Pinot. All the indexing, including StarTree index, is actually best fit for doing aggregations on very large scale of data on external tables.
Yeah, I will paste the StarTree index blog, but aggregations are where you need to look at all the records, right? And the StarTree index gives you a way to avoid that and pre-compute based on your SLA requirements, right? It kind of gives you the best of, for lower cardinality, I don't want to pre-compute, I want to compute in line. For higher cardinality, I want to pre-compute, so I'm not spending as much time during query time, right? So you can optimize how much compute you want to use at query time using StarTree index, right?
Yeah.
Thank you. Thank you for the shout out, Rishi.
I did see another question on comparison of
StarTree
ingest.
index is supported on external table. There was another question. Yes, StarTree index is supported on external table.
Yes. Maybe I'm looking at I'm looking at the chat here. I can't see any of these questions.
You're looking at the chat. The Q&A is different.
Oh, I see. Got it. Okay. In the chat, there was a question on ingest throughput and data freshness. I did point a blog. Let me put it in the Q&A as well. We did benchmark this in the against ClickHouse for measuring freshness for both upserts and non-upsert use cases. You can go take a look. But yeah, Pinot today in production, we're able to do less than 5-second freshness, as Uday mentioned.
Yeah, I think we're running short on time. So I would strongly encourage, if you have data that you would like to take it for a spin, reach out to us. We'd love to give you an environment so you can try it out, or we can showcase it to you in our cluster. Whatever is easy. So if there are no questions, I think that's all there is, right? Perfect.
Perfect.
All right.
Awesome.
Thank you.
Thank
Thank
you.
you, everyone, for jumping on.
Have a good one. See you.